Hello, everyone. Good morning, good day, good evening, maybe for someone. Okay, while I think we would wait a few more minutes for a proper webinar to start, but I think a few introductory notes. So here is some terms we would be using a lot throughout our webinar. So if you're familiar with them, great. And if you're not, please check them out. We're talking mainly about machine learning and how you can start doing research and how start using it in your business. And even if you're already using machine learning algorithms, how you can productize that using InterSystems IRIS and how its interoperability and analytics capabilities can help you with that. We'll talk about ML Toolkit, which is a wide range of tools, technologies, algorithm use cases which are available. Two of them are publicly available on OpenExchange, which is an open catalog of InterSystems-based solutions, applications, frameworks, and so on. So there is an R gateway and Python gateway which you can download there. It's open sourced and it's free for everyone. But we also have a GitHub user group, which is a private GitHub repository for user collaboration, analytical process, use cases, anonymized data, installation guides, and so on. Write us an email at mltoolkit@intersystems.com and we would add you. Okay, so let's start, I think, with the webinar. Enough time since the start have passed. So our webinar Machine Learning Toolkits for InterSystems IRIS presented by me, Eduard Lebedyuk, and my colleague
Sergey Lukyanchikov.
Okay. And what are we going to talk about? So let's start with IRIS as an orchestration tool for mathematical modeling, mainly based Python and R as mathematical modeling environments, and how we can design intelligent analytical process using IRIS interoperability with Python and R. Then we would talk about IRIS as a standalone development platform, because there is a wide array of IRIS native algorithms which you can use for mathematical modeling without leaving IRIS at all. After that, after we have run our mathematical modeling algorithms, there will be a lot of artifacts, tables, graphs, widgets, maps, and so on, and you can visualize and explore them with IRIS Analytics. And finally, we'll show ML Toolkit use cases. There will be a live demo, a free of them, so don't leave us early. Okay, let's start with IRIS as an orchestration tool for mathematical modeling. And our architecture can be presented as follows. Let's start with Python. At the core, we're using Python C API, which is essentially what's the language in which Python is implemented, actually. And we're providing an ObjectScript API, which is a one-to-one mapping for some of Python C API methods. So if you have an application written in ObjectScript, you can add parts of it using ObjectScript API to Python and invoke Python code like this. But mainly and more importantly, we're offering an interoperability adapter, which you can use in your interoperability productions to perform a wide range of tasks, all generalized, so you don't need to subclass if this interoperability adapter allows execution of arbitrary Python code, whatever you need. So in a logo and maybe more user-friendly way, we have InterSystems IRIS that platform, Python, But the main advantage and interest in Python language and in R language and in languages like this is a wide array of libraries they offer. You may be familiar with some of them or all of them: Pandas, Learn, TensorFlow, NumPy, and many, many others. For R, we're using RServe library, which is a binary TCP-based R server. There is also an ObjectScript API and interoperability adapter. So they're similar and you combine all of them. I would talk more about that, but it's really important because you can combine. Your process must not be only in R or only in Python or only in ObjectScript. The infrastructure we are presenting today and we're offering, it allows you to combine these free tools, maybe more tools in the future, to build the process you need from any combination of these languages. So what are we actually offering on an interoperability side? As you can see, there is not that many functions, but they offer much. First of all, you can execute code. So arbitrary Python or R code, you just write it up, type it up, and send it for execution. You can get variables back and send variables into mathematical modeling environment. You can transfer primitive variables, you can transfer data sets. There are a lot of utilities for that. And finally, there is error management. So if something went wrong, you know what happens, where an exception occurred, what's the exception, what line thrown an error, and you can easily fix that. And finally, for Python, we have an ability to save Python context to IRIS and load Python context from IRIS back. So for example, you can run a job which built a predictive model, save it to IRIS, and later spawn 100 other jobs and load that model into them directly without retraining it. Okay. So these tools, this interoperability adapter can be used to build business process. On this panel, you can see how a business process editor looks like. It's a web-based application. You just drag and drop the building blocks, which is some small parts of Python process and just general business process elements. You combine it however you wish, and InterSystems interoperability here works as a driver and the orchestration engine for your adaptive analytical process. You build your blocks from queries, from SQL, from Python code you want to execute. You send it from execution, you get results back. Based on these results, you can decide where you want to go. Do you want to continue with this transaction, or maybe it's bad enough you want to send it to a human workflow subsystem. All my IRIS interoperability is available here, and you can leverage Python or R predictive capabilities to drive your business process. On the other hand, IRIS offers standalone IRIS native algorithms. You can check them with Class Explorer. It's Deep C extensions package. Here's how they look like. It's ObjectScript objects. You can create them, modify their parameters, and run their methods for execution. Here's Clara clustering analysis, and you can easily save results to PMML, which I'll talk later, or into IRIS directly. Here's the results of the output. We are using PMML here, which is a predictive model markup language interchange format, which allows you to transfer models, predictive models, between different environments as long as they support PMML, and IRIS does support. It's useful. We can use it for Python 2, but we can actually do more with Python and R. So here's what IRIS native algorithms offer. There is quite a wide array of functions, actually, from basic statistical function to matrix to clustering to factor analysis. You can start data processing, and you can definitely do data preparation for further analysis. And if this set is not enough for you, you can use external tools. The advantage here for using internal tools is speed and integration with existing platform, of course. So for IRIS offerings is PML for lit1 support. So any models produced in this format from external tools can be loaded into IRIS and executed natively right inside InterSystems IRIS. The models go from regression to neural networks to everything in between. As you can see, it's a fairly wide array of model types which are supported. The import can be done either by user interface, we'll see it on the next slide, or programmatically. Here's how it can look like. You import PML into a class, choose a model, provide the data set in the form of SQL query, and you can see how it works, what's the distribution of predicted versus actual values on a testing data set. It's a UI tool. And of course, with IRIS Analytics, you can capture other outputs such as tables, such as widgets, data points, maps, map points. And with IRIS Analytics, you can visualize them for user so they can explore how they work and how they look like. And now I'd like to pass the microphone to my colleague, Sergey Lukyanchikov, who would show you ML Toolkit use cases.
All right, thank you, Ed. So before we have three practical examples to look at today. Before we start the first one, and I'll be like jumping back and forth between the slides and the demo environment, so please forgive me for that. What I'll do, I'll start the last one, because the last one is probably the most industrial in its nature. It has a lot of data behind it. So by the time we'll be finishing the first two presented, the third one should be ready to show. So I'll just save some time for our interactions. I'll just start first. I'll start and forget. And all the outputs that those processes will be generating will be put on a special folder on my computer's file system, so I can always get back and check what's the output from the process execution. So I'm waiting till it starts steadily. This actually last use case. We'll check quickly that it's log file. Here it is. So its log file is just starting to be built. And now I can get back to our first practical example. So this one is called campaign. This is devoted to a very common task with probably every company on earth, and it's marketing campaign. How to make sure that we are finding the maximum gain audience for a marketing campaign. So maximum gain in this case, in this context, means that we would like to select from the people available for sending invitations to a marketing campaign or being contacted via various channels. We would like to make sure that we put the audience that maximizes profit, expected profit from our marketing campaign. In this screen, and that's also the usual setup for that kind of tasks, we have in the upper part of the screen we have a history of the previous marketing campaigns. Each row in the table representing a respondent, and then in the response column, which is second from the right, we see the result. It should be either 0 or 1. In the lower part of the slide, we see a new selection of potential respondents. And we are asking ourselves the question, which of those new respondents should we include in the campaign? But that's not everything. In a real life situation, we would also consider at least a couple of other parameters, which are revenue per prospect, that is the expected revenue that will come to us if that prospect responds, and the cost per prospect, which is the cost that we incur while contacting any respondent, regardless of whether he responds or not. So that creates for us a setup for looking for an optimum audience, and we proceed by using our history as a training audience data. So in this particular example, it will be watching in a minute. We have 40,000 unique prospects. On the training side, we will need a fresh audience to test our model on and to draw conclusions on, which is called a tested audience. And we have another 40,000 unique prospects in that sample. So the first step we are doing in our use case, we are applying classification and regression model, or to be more precise, a stack of models to be sure that we're selecting the most proper one. And we model actually the probability of response per respondent. This is a classification task. So the probability is a kind of formula that is built based on weights and those variables that we have in our data set, starting from education, age, and going through all the descriptive variables that are available to us. So once we have an estimate of a probability of a specific respondent to respond, what we can do, by involving the cost and revenue assumptions on the one side, and applying a expected profit simulation as the next step in our use case, we can simulate the expected profit, and this is going to be the gain per contact multiplied by the probability of response less loss per contact, then the probability of non-response, so to speak. In this way, we are obtaining the so-called profit ranked audience. So we are obtaining next to each potential respondent, it's his or her expected profits, by which we can rank that audience, and already on that ranked audience, we can do the search for maximum profit, and by this defining our optimal audience. So with this introduction in mind, so let's switch to our IRIS data platform. Let me check quickly how our already started process is feeling. He's okay, he's running. So what we do here, we have a visual processes designer that has been covered briefly by Eduard. Now let's take a deeper look, a more precise look at how the processes are built using this visual designer. So what we have here, we have a whole sequence of steps and some controls that allow us to actually control the execution and branch out certain flows in the execution of this stack of mathematical models that starts from the start and ends in the end. And let's just give a quick view on what's in each step. So for example, we start from importing all the libraries from Python that are needed to do the mathematical part. So if I click here on that button, I see that it opens for me only a portion of the code that is responsible for actually importing the necessary libraries. In the next steps, and here I have a sort of branch, I'm supposed to load the two data sets, the testing and the training sets. And I'm using for this a special type of requests that is being added together with the Python gateway extensions to your IRIS that allow me immediately from this graphical process to query and to receive the result set coming from a table in the IRIS platform. Similar approach here. On the training branch, what I'm doing also, I'm implementing a split of the training set into two portions to give me two separate samples to train, on the one hand, the linear regression model, and I initialize that linear regression model here, and then I distribute it over the various pipelined models next. And I need another portion to actually train the classification algorithms that are pipelined with linear regression. So for example, I have random trees plus linear regression. So for random trees, I will need a separate sample of data, training data, to make the whole case actually valid. I'm also implementing here the random forest plus linear regression, another pipeline, and I'm also having a gradient boosting method combined with linear regression. So all of those are easily inspectable, and I can control the portion of the Python script that actually controls each particular step here. That's not everything. To make sure, I also include in that competition the pure classification modeling methods. I add a pure random forest and I add a pure gradient boosting. So with those 5 models, I'm running a sort of competitive modeling run. And the model that shows me the best so-called ROC curve, or ROC curve, the curves that we'll see in a minute generated actually by the process that allow me to compare the quality of prediction given by each of the 5 models. I'm selecting the model with the best ROC curve, and I proceed into calculating its confusion matrix. That's the sort of instrument to control the mistake that is given by our non-ideal model, however ideal it shows from the ROC curves perspective. What I do next in the process, I'm iterating through various pairs of, I'm going to that portion here, to the various pairs of initial assumptions on the revenues and expenses per contact to make sure that the scenario that I receive is the one that holds, and actually I have the nice variability of my audience depending on what are my cost and revenue assumptions. So this is done in a kind of for each loop, and inside that loop I can actually put the step that I would like to be looped over and controlled by the process in IRIS. Finally, one of the most probably important steps here in this story, it's the context capture. So at this stage, what we do, we make a instant snapshot of all the variables and all the objects that are generated till here in Python's process. And we are acquiring that content and we are saving it as a set of IRIS variables inside our platform to be further harvested. So harvesting in this context means that we inspect the previously saved Python objects and variables, and we can work with them using ObjectScript, which is a native development language of the InterSystems IRIS data platform, and we can extract the necessary knowledge and the necessary information from those X Python objects to be reused or to be applied for something else. So here in this last step, you see ObjectScript. In this case, yes, we are acquiring it in a JSON format. So this is a very brief overview, and let's see it working. I'll close that previous processes startup window, and I'm navigating to my campaign process. In order to start it, like everything in interoperability part of the IRIS platform, so I need to send it a message. So in this case, I'm sending some generic message, and this is an important portion of the platform functionality, which you can rely upon when you make a productive implementation of your Python or R models. So you make your models actually interact with the outer world, and IRIS is the kind of broker that manages the messages between the outer world and your model. So I've just launched it. It's working right now. Let's wait for a couple of seconds more. This one is really short compared to the previous one, which continues working. I can judge it by the fan speed on my laptop. Just a couple of instances more. All right, it's finished working. I can quickly inspect its visual trace. So I see that every step that I had in my graphical visual design is now being presented as a request-response pair. For example, we started from importing those Python libraries, and I see them on that log as a specific portion of the Python code sent to Python. We can also check the last step, one before the last actually, which is the capturing of Python's context. And I see the request to capture, as of this moment, what exists in Python's context. And I receive back the ID in the global database of IRIS, telling me where I can find the saved Python context. So now if I go to my directory, so I see a bunch of graphical files generated here. So let me start them one by one. So what I see first, I see the ROC curves from my 5 models. So the ROC curves are presenting actually the quality of classification given by each of the models, and they look pretty much alike among themselves. But if we do a little bit zoom out by going to another graphical file, so we see that at least the green one and the violet one are giving the ROC curves that are farther from the x-axis. Probably we should continue with one of them. So the choice is made by the process in this case. I don't see it's being made explicitly, but we continue with one of them chosen. And then the other charts are actually showing us the process of scenario testing. So we start from the initial assumptions of $1 as a revenue per contact, and we have 20 cents as an expense per contact. So then the audience is given to us by that. The optimum audience is given to us by that dotted red line. So in this case, if we read it from left to right, that should be something like 45 most profitable respondents, and the expected profits we know because the model has calculated for us. So we can get the exact names for those top 45. If we a little bit reduce the revenue and pump up the expenses, what we see our model giving us slightly different results. So we need to hunt for only 40 top most profitable contacts. And if we continue that exercise, and by the way, we see in that graph that if we include all the people on our tested audience on the campaign, we'll have a guaranteed loss. And if we continue, we'll see that starting from if our revenue is equal with our expenses, it makes 0 sense actually running that campaign. So that is the first story that I wanted to show you. So let me get back to the next one. And by the way, before we get to the next one, I'll just say a couple of words about the applicability of that campaign story to the possibly other industry scenarios. So for example, so we start with marketing, and this mechanism that we've just seen helps us to answer such a question as who to include on the campaign to maximize potential profit from that campaign. We can apply a similar mechanism, for example, for public services, and look at the following question: who to contact to maximize the result from the awareness campaign for income taxation changes. This can be also customer service domain: who to involve in a recall campaign for a potentially defective product. Or this can be supply chain management with a question like, for which item inventories should we use order pegging, and for which items a reorder point will be okay. So however different those formulations may seem, they could be approached using the mechanism that we've just seen. The business benefits. First of all, we have a probability-based simulations and optimization. So we are estimating in silico, that means without touching anything in the physical world, the economic effect of potential decisions. Technology-wise, IRIS leverages for us the cognitive capability by extracting and interpreting and integrating the so-called knowledge-rich objects, models, graphics, rules, etc., from modeling environment and services. So now I'm switching to another example, which is based on R, and it's coming from the healthcare domain. So in this example, we are modeling the so-called patient travel or patient migration phenomenon. It's when people that have specific diagnoses are forced to leave their home city or home region to travel to another city actually to get a qualified treatment. So in this setup, what we have in the left, what we see in the left part of the slide, we see the master data for diseases. And actually after the letter D and underscore, you can see the international disease code following them. So like that, we have 20 most patient traffic heavy diseases in the country. It's a countrywide case. And in the upper part of the slide, we see a sort of matrix. And in the header of that matrix, we see the codes of specific region. Letter L means location, then we have the underscore, and then the coded anonymized location. And we also have the top 20 locations in the country that attract the most of patient migration traffic. So at the crossing between the disease and actually the location that receives the patient traffic with that disease, whenever we have that traffic beyond the average value, we see 1. And if it's below average, we see zeros. So this matrix allows us actually to capture the most important patient migration flows in the country for specific diagnoses into specific locations. We will do our modeling for this use case using the so-called graph models. So we'll be using a bipartite graph, and the graph is bipartite because the nodes, the vertices in that graph are diseases and locations. There are 2 classes of kind of nodes. We'll have edges that connect those diseases to those locations, so those vertices to each other. And after having run some sort of descriptive analysis of the bipartite graph, we will make our algorithm detect the so-called communities, that is the combinations of the locations and diseases that are highly linked and could be seen as sort of drivers beyond the phenomenon of patient migration in the country. Okay, so at this point, let me get back to my IRIS. So this is the log from the previous process. I close it. I'll check my ever running third case is running. It's good, no problem. So let me first, as in the previous case, inspect the graphical design of my use case process. So I'll go to the diseases process. So again, what you see here is a graphical flow. We have 2 requests that are very similar to what we've seen in the Python previous case, that query in the data from Python, from IRIS tables. But starting from the next step, we already start seeing R. And this is the language that is called the development language in R statistics environment. So we see that R script starting to show. And step by step, by working and preparing and transforming the data that we've seen in the slides, we are first preparing a graph. So we run here the commands that build from that matrix, that formal presentation, tabular presentation, a graph. We visualize that graph in several projections. So we can see separately the links between the diseases. We can see the links between the cities. We analyze that graph, and in particular that graph's nodes, vertices, in terms of the traffic intensity that is coming in and going out from those vertices. And based on the intensity of those links, we are making that algorithm actually detect the communities. So instead of watching through all different scripts and actually going through formal logic, let's run it and take a look at the graphical example. So I'm moving to my diseases use case, sending it a test message, and that test message may come, it comes from me in this case, it may come from an external system and make it turn, actually run it in a perpetual mode. Runs very quickly. So as in the previous case, I also have a full log for this process. So it starts from some SQL query request, and it goes through all the various pieces of R code being sent to R. And my R is here. It's being turned in the background using the rserve component, and receiving back the responses from R, and actually saving the results in graphical files. So let's inspect our graphical files. So you see my third use case already starting to produce the outputs, but we're interested in our second case's outputs. So I start the first graph. So that's a projection of the bipartite graph on the disease axis. So we see the links, and the links mean the traffic via specific locations of the patients with those diseases. So those diseases are kind of linked to each other because the people with those diseases are kind of traveling to same locations to receive treatment. We see another projection, a projection on the locations axis. And we immediately have some useful results, seeing that although the bulk of the locations are linked to each other in the country, there are two outliers. And those may mean some sort of endemic areas where people either have little access to external help or the diseases can be treated locally. So in either way, it's a good point to actually to inspect them in a more deep fashion. So we see the bipartite graph itself. It shows in the blue rectangles stand for diseases, the orange or yellow one, depending on the color scheme, stand for locations. We start calculating the intensity of the links, and depending on the number of edges that are connected to each of the nodes on the graph, we make it bigger or smaller in terms of the bubble size. So immediately we start seeing some candidates for forming communities around them. We can instead of a graphical approach, we can also apply some numbers-based approach. So we see a distribution of the so-called node degree. That means of the number of the links that are connecting that node to the other nodes on the graph. So we see some outliers clearly shown on the graph. And finally, the algorithm generates for us at least two big and distinct communities. The first one actually accumulating different locations with some disease next to them. So those are the highly linked locations with probably a disease that sends people to those locations. And we also have another cluster, another community consisting of a number of diseases and one location to which probably the people are traveling with those diseases. So this is the stage which could be actually in the analysis process that can be informative enough actually to be analyzed by further models and further experts. All right, so this is the second use case, and I'm switching to the last one. Try to go quick to leave some time for our questions. So if I check now the log for my third one that has been running all the way through my story till that point. So I see that this log is now completed. And instead of inspecting the log, let me start from the graphical part. So I go to the graphical definition of my engines use case. And wait a sec. Check the right version of it. Yep. And what strikes us from the very start of where we're looking at this graphical definition, we see no scripting language, no Python, no R. Why is that? Because if I step on each of those bricks that actually are doing the most important mathematical work here, I don't see Python, I see ObjectScript. So that comes from the portion of Eduard's presentation where he was covering the native capabilities, mathematical capabilities of IRIS platform. And to implement that use case, and I'll tell in a second, in a couple of words, the story behind that use case, I'm using the native PCA, the principal component analysis, and I'm using the clustering methods that are coming from IRIS platform. No Python, no R is employed here, till a certain point in the process. So, in a couple of words about the story behind this use case. We have engines that are working a random number of standard cycles. The cycles can be weeks, can be days. So what we have 100 engines to which sensors are connected, and per each cycle, per each standard operational cycle, we are receiving a sort of aggregate reading per engine and per cycle. So based on those readings, we ask ourselves the question, what is a condition of specific unit of my equipment? So for each engine among those 100 ones, I should be able to tell in which part of its life cycle it's currently residing. Is it in the beginning of its life cycle? Is it in the middle, or is it closer to the end? And I should be preventing the immediate failure of it. and my repairs and maintenance specialist should visit this particular engine. How we do that? We split the population of engines in two parts. One is used for training our models, and we select some 50%, random 50% of those engines. And the other 50% we use as the kind of application of applied data. So we apply our models on those engines to see and to validate our models. The first modeling step is PCA, the principal components analysis modeling, to navigate from several tens of specific sensors, several columns, tens of columns standing for each specific sensor, to reduce them to a operable 10 or 12 columns that represent that wide data set. We do that in order to be able to apply clustering model. So we will be doing the training and the application of clustering model using the training and testing and application data sets in which the original sensors are replaced by the principal components. So we'll be applying clustering algorithm, and the clustering algorithm's objective is actually to split all the moments in the life cycle of a specific engine into three distinct portions: the beginning, the midlife, and then the end of the life cycle. So with this in mind, what we've done, we've just in the beginning of my part of this webinar, we've started that use case. It has been working behind the scenes all the way till now. So what we can do, we can revisit our file directory and go through the graphical outputs produced by this model. So those graphical outputs are going in tuples, one standing for the training data set and the other one for the testing data set. So this diagram, this scatter plot, is actually confirming for us that the number of cycles worked by each engine is random, both in the training and in the testing data set. So we can calculate a distribution of engines per length of their life cycle. We also obtain something more or less empirically classical, so to speak, for both samples. What we do next, we run some correlation analysis on our data sets to see whether we have some highly correlated sensor variables, some inputs, and we try to exclude something that is too highly correlated in order not to overfit our models to something that is excessive for the analysis. So finally, what we do, we visualize the end results of training of our model, clustering model, on a specific sensor, in this case, sensor R02 on engine number 1. So we see some expected result. It has splitted from the point of view of this particular sensor and the parameters that it measures, it has split the life cycle of this particular engine in two distinct parts. The mid part is represented here also, but it's very short. If we take a look at the other sensor, we see all the three parts of the life cycle, the three stages of the life cycle identified. So depending on the sensor, they can be more or less presented as the outputs, but we do have them, formally speaking, we do have them in each of the outputs in the training portion of the model. If we now go to the testing data set and we apply the models that have been trained, so we see that the models, without knowing actually how many cycles a specific engine will last, they color for us the cycles in the lifetime of that particular engine by applying the knowledge they have learned from the training data set. So we see the engine 2 with sensor R02, it has been colored in a interpretable enough manner to actually to see that when the yellow phase is ending, it's time to actually to think maintenance or replacement of that engine. Same example for another sensor on engine number 50, and another sensor and another engine. So with that, I would say we're at the end of the practical part of our today's webinar. So we hope you enjoyed that brief demo of our platform's machine learning capacities. And we are open to your questions that we hope have been put on our chat today. So thank you. We would like to switch to the chat to actually go through the questions. Janine and Emma, if you could assist us.
So there was one question that was sent in online that I assigned over to you guys, Sergey and Eduard. So if you want to address that one, you can go ahead and do that in your questions vein.
Okay, wait a sec. Yeah. Here, I'm reading through the question. Here we make a blanket around the IRIS native algorithm. What does this phrase mean actually? The IRIS native algorithm is something that is supplied together with the IRIS platform and is presented to you as a method, as a class actually in IRIS that you can use without going to Python or R. So basically, when Eduard was running through his portion of the slides, he presented a more or less full catalog of those IRIS native methods, and two from that catalog, the PCA, the Principal Components Analysis, and then Clara clustering, we've implemented and have shown as the third example of today's webinar. So to work with those IRIS native algorithms, you just apply ObjectScript and you call those classes as you would do with any other classes in IRIS platform. That's why we refer to them actually as IRIS native. Nice presentation. IRIS is very powerful. Thanks. Thank you. Thank you. We've been working on that tool set for, let's say, last, if we took all the development cycle for the last 6 months, going through different stages, and we have several people giving us their kind permission to install it for them. Some of them probably even present on that webinar today. So double thanks to those who were bold enough. At least I've seen a couple of companies that are present on that webinar. We're in the process of rolling it out to some partners of ours, or the people that are using IRIS to deliver digital services, and those are probably currently the most active segment of the users of those extensions. So this is something that is not only a theoretical exercise. If we go just through the slides and carefully selected examples, but it's also something that is working in practice, and we have quite a busy support activity linked to that prototype. On the slide that I'm projecting, and while we are waiting maybe for some other questions from the audience or on the microphone, whatever. So again, to reiterate, we have a publicly available catalog. Wait a sec. There was something about the R serve, but I'm not sure we are retaining that question, Janine. While we are waiting for that question to probably reappear, so the person that has been posted it, please post it again. Eduard, yes, please.
So the question is, what do I need to run rserve? Yes, that's correct. You need to install the R language, obviously, and you need to install rserve library. You can check the R gateway at OpenExchange. It contains a complete installation instructions, so you can just follow them, but it really takes just a few minutes. Install R, install one library, and load code into IRIS, and you're ready to go. So it's really a fast process for both Python gateway and R gateway. It doesn't really take that much time. And if you're familiar with Docker, you can start running Python gateway immediately by just pulling a specific image. It's already pre-built. Just pull it and it's ready to run. No installation required at all.
I would add to that to what Ed has just said. We have a full detailed manual in that user group, which could give you let's say alternative ways of how to proceed with the installation. So if you are interested with something that is completely step-by-step and self-paced, also please send us your coordinates on mltoolkit@intersystems.com, and we'll include you on the private repo, which contains the full documentation, full set of examples, including the examples that we've been showing today, and where you could also discuss in a private company with people that are really interested and represent the audience that is interested by those extensions, ask your questions and present your situation and obtain methodological help. Any more questions?
Bye, everyone.
Bye-bye.